Good day to all of you, and welcome back to this class on geoenvironmental engineering or environmental geotechnics. If you recall, we have looked at liners of landfills, we've looked at covers, and we have also looked last time how we extract the leachate from the base of a landfill. And today we are going to look at how we extract the landfill gas which is generated inside a landfill. So if I presume that the cover of a landfill is impervious and the liner is impervious, the cover may or may not be impervious. For example, the municipal solid waste covers may have clay in them but may not have a geomembrane, so they may allow some limited moisture into the landfill. But presuming that both the cover and the liner is impervious, we have a balloon, right? And if inside the balloon gas is being produced by some reactions which are taking place, what will happen to the balloon? Yeah, it will start off become bigger and bigger until one day it will go bang. So that's what we have done. We put a cover, we put a liner. From the bottom we are taking out the leachate, but what about the gas? So remember, as gas is generated, it creates pressure and therefore it wants to come out from somewhere. So if you have a balloon and if you make a pinprick, what will happen? Quickly the gas will come out and the balloon will deflate. So we need to see how we collect this gas, because if you make a pinprick, the gas will go out into the atmosphere. You can't run after it and say, all right, let me just collect it and treat it. So you need to allow it to come out of a pathway where at the end you can do whatever you want with that gas, right? So in the case of a leachate collection system, what happens? The leachate comes out from a well or from a side slope riser, and then it goes to a leachate treatment plant, which may have a holding tank where the leachate will be collected, or it may go into a tanker which takes it to an off-site effluent treatment plant. So what do we do with gas? Let's have a look. Okay, we just remember this cross-section that we have. Gas is being generated here. It will put pressure on all sides. It will put pressure here, it will put pressure on this side, it will put pressure downwards, and wherever it gets a preferential path to come out, it will come out. So if you don't put any preferential path in the cover, the gas will have a tendency to come out through the leachate collection layer. Why? It's a high permeability layer. As long as the high permeability layer is full of water, the gas cannot come out. But if at any point of time the leachate collection layer does not have leachate, there is preferential path for the gas to flow out. So we will look at the following aspects of gas. What are the constituents of landfill gas? What kind of quantities are generated? What are the venting and extraction systems? And how do we treat? Once we've collected the gas, what do we do with it? So first let us remember that in municipal solid waste landfills, which has got significant biodegradable content, food waste, paper, wood, leaves, gas is generated as a product of waste biodegradation. And that's a significant amount of gas. Plus there are other minor constituents. I mean, from your household, if some nail polish is coming out or some acetone is coming out, that's a volatile organic compound. So there will be some volatilization of the household chemicals, something if some paint thinner is there. All these things you can smell. So these are all volatile compounds. So those are minor constituents, but the main gas is from waste biodegradation. In other landfills, there may be no gas or negligible amount of gas. For example, if you have construction and demolition waste, it's not going to produce any gas. If you have hazardous waste, it will depend entirely on the amount of organic content in the hazardous waste. If it is inorganic hazardous waste, it may have very little negligible gas, or it may have some VOCs, but otherwise you will not have significant quantities. However, if the hazardous waste itself is also biodegradable and comes from a industry which is dealing with such products, then you can have gas. So what we see is that when you bring waste to a landfill and you spread it out, then biological degradation of the waste occurs in the presence of oxygen. The void space has oxygen in it, right? And the aerobic bacteria are able to react with the waste and give you aerobic decomposition. But the waste fills up rapidly in a landfill. So once the initial oxygen is removed or utilized, then no more oxygen comes in, because you are putting a daily cover, a cover at the end of the day, a soil cover at the end of the day, and the waste gets buried. So later anaerobic bacteria take over and we have anaerobic degradation. So if you look at anaerobic degradation, it is in the absence of oxygen. And if I took at one of the biodegradable components, which is cellulose, then the reaction is something like this. It's a very simple equation. I'm not looking at lignin, I'm not looking at other constituents, just a simple equation, and what you find is you form methane and you form carbon dioxide. So this is anaerobic. If it was aerobic, there would have been an oxygen content here and there would have been a different product of the degradation. So just to re-emphasize, when waste is spread in layers, oxygen is present in the void space. In the presence of oxygen, aerobic bacteria take over. They generate water, carbon dioxide, organic acids and inorganic minerals. But the depletion of oxygen results in the anaerobic decomposition process taking over. And the principal gas produced in the initial phase is carbon dioxide, but with time methane increases, reaching a plateau. So you have this mix of carbon dioxide and methane. So if you put in a gas extraction well in any of the landfills, out will come some methane and carbon dioxide. Methane is combustible. So if you go to a landfill and put in a little pipe and you take your matchstick and put it at the top of that pipe, a flame will come up just like in your kitchen, and that is the methane gas which will be burning. Of course, you should not do this, because by doing this you might send the flame inside the landfill and the landfill may start to burn and you may not be able to put it off. In your kitchen you can put off the flame by turning off a knob, or on the ground surface you can put off a flame by covering it with soil or with a fire extinguisher. But once a flame goes into the landfill, it will smolder inside, no matter what you do at the surface, unless you can go after the flame into that pipe which you put, the landfill will remain on fire. So all these issues about burning landfills accrue to the fact that methane is inflammable and it will burn if it gets access to a spark from a human being or from other. So if I look at the way the processes are, if you look at this, first is the aerobic phase, right? In the atmosphere, what are the main constituents of which are the two gases in the atmosphere which are predominant? Nitrogen and oxygen. So nitrogen is very high, oxygen is high. In the aerobic phase, they both deplete. And then the anaerobic phase takes over. Now there are subsets of this phase, we need not go into details of this, but what we see is that carbon dioxide is formed and slowly the methane begins to form and eventually methane is generated for a larger period of time. So you have these methogenic phases 3 and 4, and aerobic may occur later if ever there is access to more oxygen. And in terms of how long do these reactions occur? Well, the aerobic phase may be a few months. Aerobic phase may be a few months. The anaerobic phase may be some years. Whether the anaerobic is slow or fast, there was a H2O in the equation, if you recall, the previous equation we saw. So if you give access to moisture, it will degrade faster. If you don't give it access to moisture, it will degrade slower. So if you have a landfill with adequate moisture and something like a bioreactor landfill where you are recirculating the leachate, it's a landfill with adequate moisture, and therefore it will give you a lot of gas, but it will give you gas for a short period of time. And what is this time that I am talking of? Maybe 5 to 10 years. So a bioreactor landfill may give you a lot of gas for 5 to 10 years or little more. However, when we do daily cover and we make a dry tomb landfill, no moisture is available. So the process of degradation slows down, and therefore this graph shows that the peak is no longer there. It's a much lower production rate, but it lasts for a longer time. In a sense, all biodegradable material has to biodegrade. So if you look at the area beneath this and you look at the area beneath this, they have to be similar. So a dry tomb landfill, the way we are discussing it, may continue to give you gas for 20 to 25 years. So it may not stabilize that fast. But remember that gas peaks and gas then slows down. And if you look at the major constituents, as I said, methane and carbon dioxide are your major landfill gas constituents. So if you have a municipal solid waste landfill, you have to have a very robust gas extraction system. The other gases which you will get in a municipal solid waste landfill are nitrogen, hydrogen ammonia, hydrogen sulfide, oxygen carbon monoxide, and as I said, some of the trace volatile organic compounds. And if you were to analyze a gas sample from a landfill, it would have this kind of constituents. We said methane and carbon dioxide are the most predominant, and they will be in the range of 30 to 60% depending on whether you are in phase 2 or phase 3. Phase 2 carbon dioxide will predominate, phase 3 methane will predominate. Others are very lower, please note. And all these trace constituents are now down to less than a few hundred ppm. Okay? But you can detect all these. So that are the kind of gas. We are interested in methane for 2 reasons. It's a greenhouse gas. So we don't want to allow it to escape to the atmosphere, and it is highly explosive. Occasionally it will accumulate in basements of nearby houses and boom. So there are, if you look through literature, a few tens of incidents of explosion. It will not explode in the air. In the air it will burn. But if it keeps on, if you have a house, let us say 300 meters away from a landfill which has a basement, and somehow a preferential path forms between the decomposing landfill and it goes to that basement, it will accumulate. Once it accumulates and once it reaches a concentration of more than 5%, 10%, you can have an explosion. So that's the problem with methane. And it's because it is combustible, you can recover energy from it, so you should. Carbon dioxide, of course, is also colorless and odorless. One thing I also want you to note is that methane is lighter than air. Methane is lighter than air, and carbon dioxide is heavier than air. And so if carbon dioxide is heavier than air, it tends to sit down in a landfill. Methane is lighter than air, it tends to go to the top of the landfill. However, if it's a balloon, even if you have a heavier than air gas, eventually wherever you make the pinhole, it will come out. because it would have accumulated under some pressure. However, if carbon dioxide mixes with water, it will increase its hardness, and H2CO3 one can talk about, so pH will go down. So it does do groundwater, it does affect the groundwater if you are not got a good liner at the bottom. But our main aim is, if I burn methane, it becomes carbon dioxide, right? CH4 plus O2 will give you CO2 plus H2O. But carbon dioxide is also a greenhouse gas, but much less effect. So methane is supposed to be 21 times more, have more greenhouse effect than carbon dioxide. Okay, what about gas quantity? As I said, under normal conditions, the rate of gas production reaches a peak within a few years. And we'll look at the rate of production in the next slide. And it tapers off. But in a dry tomb landfill, gas may come out for 25 years. When moisture content is limited, gas production is more flattened out. When moisture content is high, the gas peaks up earlier. So if I look at literature, because there are a lot of models which exist for gas generation, and which model has anybody been following a model for landfill gas generation? Mohit, have you done anything about landfill gas generation? Well, there is a US EPA LandGen model. You can Google it. It's a free software. The problem with all these models is they don't give you very accurate output because of the heterogeneity of the waste, and the fact that inside the municipal solid waste, it's not like a controlled environment. You are doing this biodegradation in a reactor in a factory, you can control everything. pH, temperature, oxygen, moisture, everything can be controlled. How much is it in the vessel? But if I am doing it in the landfill, nothing is controlled. So it's taking its own pathways. The waste which is coming is heterogeneous. It is coming from so many households and so many markets. So it's sometimes difficult to get an accurate estimation. You can get a very variable estimate, but a variable estimate is better than having no estimate. So if you look at literature, the rate of production of gas is typically 1 to 8 cubic meters per ton of waste per year, right? So that is what you will find in literature. And if you look at the gas production rates reported from wells, if you have a waste mass and you put a well in it, then you get 6 to 10 cubic meters per hour per well. This is India in 1 or 2 landfills. And if I look at Europe, here is 6 to 10. Here it is 10 to 20 cubic meter per hour per well. But you remember, this is more efficient system. Here, the landfill that we are talking of is a well-designed landfill with a liner and a cover. Whereas here we are talking of an open waste dump. If you have an open waste dump and you put a well in it, this is the kind of gas production rate that you get. If you have a well-designed landfill with a cover and a liner, you will get a higher output. So this translates to about 50 to 100 kilowatts of energy per well. Also look at the depth. Here they were talking of 5 to 8 meter deep landfill, and here they are talking of 10 meter deep landfill. And they are having typically gas wells at a spacing of 30 to 75 meters. So if you have 15 to 20 wells of this kind, you can generate 1 megawatt of energy for 20-25 years. That's the European experience. What's happening in our waste dumps? In our waste dumps, we have been accumulating waste. We have some huge, huge mountains. But what? There is no cover, there is no liner. And these have been all having a lot of moisture. So whatever the gas was has been generated at a good rate. And the old waste dumps therefore have significant biodegradation which has already taken place. We are attempting to take out the gas by covering these waste dumps and putting some wells in it. There have been 2 experiments, one in Gorai and one in Ghazipur in Delhi. The amount of gas which has come out has been 50% or less than what was estimated using the various models, as well as the gas extraction well tests. Before you put a set of wells, you do one well and you find out, are you getting this kind of output? Well, they got pretty good output, but what they didn't know was that over a period of time that output is not going to sustain, because that was the first well which was being drilled. Whereas these figures are coming from several wells in a well-designed landfill closed at the bottom. So currently the experience with gas extraction in India from old waste dumps has not been very great, because there is a kind of a critical point beyond which you can make an investment if you can get that much gas. But if you don't get that much gas, don't make an investment, because you won't get your return on investment. So maybe this will stabilize in a few years when we have more data. How do you control gas? Simple, have a containment system. I make a balloon which encloses the gas and prevents the migration outside, and then you have a system where the gas can come out along specific pathways for venting. So venting means you are allowing the gas to come out through pipes and leaving it to the atmosphere. So how is venting better than an uncovered landfill? In uncovered landfill gas is coming out from the entire surface and you cannot collect it. In a vented system, you have a cover, and on top of the cover there is a little pipe or sets of pipes through which gas is coming out. At the moment you don't have money to put a flaring unit, you don't have money to do, but at least you know that the gas comes out from these 10 points. And at any point in the future you can put a header pipe, join these and take them to a gas control collection treatment system. So then you need a system for flaring it. The cheapest option is to flare, because all you have to do is you burn methane into carbon dioxide. You may not recover the energy, but you can also utilize the gas for cooking purposes, for heating purposes, or for electricity generation. It's not that simple. This gas smells very terrible. It's not like the odorless gas which comes into your house in a gas cylinder. So you have to scrub it, you have to clean it, you have to deodorize the gas, and once you start doing that you get more and more sludge which is coming out because you're going to clean up the gas. So there have to be specific gas cleanup activities to utilize this gas, but it is utilizable. So when we talk of containment, the liner at the bottom acts like a containment and the barrier at the top acts as a containment. If you are going to want to extract the gas for the purpose of generating electricity, you will need a geomembrane at the top. Otherwise your gas collection efficiency will be very low. Clay is a barrier to water. When water passes through the clay, even if there are some desiccation cracks, they close up because the double layer is formed. But if you have gas and the clay is dry, it has desiccation cracks, it's going to run out of the cracks, then it's not going to swell and self-heal. Whereas clay self-heals to water. So clay is not a good barrier for collecting gas efficiently. It is a good barrier to collect gas through vents. But if you want high efficiency collection, that means if 100 units of gas are generated, if I want to collect 50 to 75 units, that is high efficiency. For that, I do need something at the top and I do need something at the bottom so that it does not escape. Right? So composite barrier has to be used, though it is not prescribed in the municipal solid waste management rules. So if you are going to say, I'm going to design a municipal solid waste landfill with gas recovery, well, you have to have a geomembrane in your cover. In passive systems, gas will come out on its own under its own self-driven pressure. You have to just give the preferential pathways. If I have a well-designed containment system, and remember, containment for gas is much more difficult than containment for water, then if I have, let us say, two vents, right? Gas will come out in these vents at its own pressure. This is called a passive system. But if I take a suction pump and start applying suction in those vents, I will take out more gas, that becomes an active system. So an active system is one in which you actively use energy, like a blower or a suction pump, to take out the gas. A passive system is one in which you take whatever comes out. That means gas will come out from here. This is a passive system. But gas may also be coming out from, there's some leak. It will also be going somewhere else. Because there is positive pressure, then only the gas comes out. Okay? Instead of this, if I have the same system, but now I use an active system. And I'm sucking out the gas or the air. What is happening? Whatever is inside this is going to this well. So here, gas used to travel and come out. Here, the gradient for the gas to travel is more. Why? Because you have a negative pressure inside this. So you collect more gas. What happens to this gas which was escaping? So since there is no positive pressure in the heart of the landfill, maybe this doesn't want to go out, it wants to go this way. So when you do active collection, your efficiencies go up. When you put geomembranes and containment at the top and the bottom, your efficiencies go up. Can I get a lot of gas by doing a lot of suction? I just now said, you don't do any suction, less gas will come out. You do suction, more gas will come out. I do more suction, more gas will come out. Why not? Well, I can't produce more gas than, I can't suck out more gas than what's being produced inside. Suction doesn't hasten the process of gas formation. You want more gas, you put in some more water. Give it more moisture. It will generate more gas and then you can take out the more gas. And suppose, like wanting to meet a target, you're a manager at the site and your owner says, okay, if you can bring me, instead of 10 cubic meters per hour, 15 cubic meters per hour, here is your bonus. So what will you do? You will tell your pump operator, thoda aur section lagao. Dada, thoda aur, put more section. Let's get more gas out of it. Let's get both of you and I get bonus. What will happen? Well, if your liner and cover is not good enough, air is going to start coming in. If you apply too much suction, what will happen? Gas is not being produced. If there are any leaks in the system, air will start coming in from the side and from the top. So you can't produce more gas, you can't collect more gas than what is being produced inside the waste. And that is fundamental. Now, both you and I are not biochemists. We don't deal with biodegradable material. We don't deal with the chemistry of it. And we don't deal with how the pH, oxygen, moisture content of the reaction gives me more gas or less gas. So the entire stoichiometry of this is done by biochemical engineers. But what I'm giving you is that what happens in landfills, what kind of figures that emerged. So in passive systems, the pressure of the gas is the driving force. And in passive systems, what do? You have a cover? Just put a gravel blanket under the cover. That means if I put a gravel blanket under the cover, then this is of course an exaggerated view. Then all the gas which is coming out will come into the gravel blanket. And then it will travel in this high drainage path to the vents. So a good passive passive system is one which has a gravel blanket at the top. You want even a better passive system, you can make the wells and fill them up with gravel. But you are not applying any suction, so it is still passive. Then the under self pressure, it goes to a closer drainage path. The moment you start extracting, that's the time then you have got into an active system. So passive control is achieved by providing drainage paths of higher permeability. Gas drainage paths are just beneath the cover or interceptor trenches or venting columns, and vents are installed through the cover system, and a perimeter trench is given all around the landfill. So very simply, this is your cover and this is your gravel or the gas collection layer, which we've already talked about. And these are your pipes or vents through which the gas will come out. They are facing downwards because you don't want rainwater to go through these vents down into the waste. So this is a passive venting system. You can see some trenches here. These are trenches for any gas from the perimeter. But for this to function well, the liner must be there so that the gas cannot go out from any other way but only come out through the top. And if I look at it a little closely, I have my waste, I'll have a foundation layer if required, a gas collection layer, a composite barrier, a surface drainage layer, and the topsoil and the protective layer. And this is the vent. Today you may allow it to vent into the atmosphere. Tomorrow if the government says no greenhouse gas emissions, you may put a header pipe and flare it and utilize it. But that is the concept of a passive venting system. You can also have wells, and if these wells are filled with gravel and there is no suction which is applied, they are still passive. You can also have horizontal drains. These may have a pipe or these may be just gravel drains with the filter criteria being satisfied between the waste and the gravel. If they come out under its own pressure, they are still passive. So this is a gas extraction well which will be used in an active or a passive case, like a tube well. Like a tube well, perforated pipe, gravel pack around it, a pipe which takes you to the top and connects to a gas header pipe. The header pipe goes to a suction pump or a blower which pulls in the gas if it is active, or the header pipe goes to a vent if it is passive. So all the gas has a tendency to go towards the slotted pipe. There is a bentonite seal here, this is not slotted, so this is the place where you are collecting the gas. This can be pretty long. This is a typical trench. The pipe, horizontal trench, waste. This is a perforated pipe, and you will have to have between the gravel and the waste a geotextile filter separators, right? And you have put compacted clay at the top. You don't want to extract air through this pipe. You don't want anything to coming from the top in this pipe. So these trenches can also be put in the waste or horizontal trenches. As you are laying the waste, you can make horizontal trenches and get your gas out. So in the active systems, you are inducing suction, nothing else is changed, and that is used to extract the gas. If you keep the system under negative pressure all the time, no methane is going to escape, and therefore your landfill gas, landfill fires will not be there. But we have to make that investment, and you have to put a cover at the top. So if you don't close your old waste dumps and you don't do your gas collection properly, you are going to continue with this problem of fires and smoke on the landfill. So the main components are gas wells or drains in the waste, pipe network leading from the wells to the pumps. Moisture is also coming out with this gas, water vapor. So you have to have condensate traps to remove this moisture, and then you have to take it for treatment or flaring. So you have pumps which induce suction, which remove the gas and transmit the gas to flares, to diffusers, or to a utilization plant. The only difference between the passive and the active is the presence of an extraction unit for taking out the gas and making everything flow towards that path. Typically the wells that we use are 1 foot to 3 feet in diameter, and these are HDPE pipes because you don't want the waste to interact with the other pipes. So you make a well, and in that you keep a smaller diameter perforated pipe with 10 to 20% perforations and surrounded by gravel packing. When a vacuum is applied, then just like you have a zone of influence in a groundwater well extraction, you remember? It will be a circular radius of influence. Exactly like that, there will be a radius of influence of each well. And that's why the spacing typically varies between 35 to 75 meters. 50 meters is very often adopted as the spacing between wells. That means the radius of influence is 25 meters. So this gives you an overview of how it looks like. So you may have in any landfill, there will be a liner, you have a cover, and you have these wells. These are the header pipes, header pipe, header pipe, header pipe. All of them go to a suction pump or a blower. The condensate, the gas cleanup, it can either go for electricity generation or it can be used for the purpose of heating or for other purposes. So what are the ways we are using this gas? Gas can be flared. No energy recovery is done, but greenhouse gas emissions are lower. It can be used directly for heating and cooking. Heating means in cold countries, you are using hot water or you are using heating systems for heating your homes. So if you have a landfill, up to a particular distance, this gas can actually be sent as a house heating gas. Or you can send it for cooking, but deodorizing is a major issue. It can be used for generation of electricity. So if you are going to use it, then you will be able to get some costs to offset the gas control systems. If you are not, if you are just flaring it, then you have to just make an investment all the time into the system. And between heating and electricity generation of course is very prominent, because you can plug the electricity into any grid and somebody very far off can take the electricity. Heating and cooking means there is a travel distance. You should be within a few hundred meters or a kilometer or two or so for making use of the heating. So direct use is more efficient than electricity generation, and energy recovery should be always considered in preference to flaring. So this is the current state of the art of gas treatment. But what is happening on the development front? People are saying, why do you burn it to convert it to carbon dioxide? Let's oxidize the methane. Can we oxidize it? So just like there are these bacteria, we have these oxidative bacteria in the soil. So normal soil, if methane is passed through normal soil, about 10% of the methane will get oxidated by the bacteria or by these microbes inside the soil into carbon dioxide. So you don't have to flare it. But it doesn't do this 100%. So actually oxidative soil covers are being developed. They may be soil only, or soil and plant roots, or soil and compost and biochar, and oxidation rates have been increased to 30% and higher. And I think not in the not too distant future, we will be having soil covers which will oxidize. The problem is replenishing. Everything has a capacity to oxidize. If too much methane will come, what will happen? Those microbes will not be able to replenish or grow, so that when more methane comes, they can do the oxidation. So there is always a replenishment time. If methane comes and doesn't come, then it's fine. You oxidize, then you regain yourself, then you do it again. But if methane is coming continuously, then it may kill the whole system which oxidizes you. That's like attenuation of capacity. So oxidative covers are now under development. They will be passive. They will have no investments. They won't be at high temperature, and they are also one of the alternatives which we may examine in the future. So gives you the overview of gas generation and what and how we control it. As geotechnical engineers, it's not so much importance for us to do the chemistry of what's going on inside, but be sure that the cap is well made, be sure that a gas collection layer doesn't mix with the layers around it. All these preferential parts, the drains, the horizontal drains, the wells, that is all that we have to design so that we can get a lot of gas and we can use it efficiently. So if you have any questions, I'll be happy to answer. If you feel there's another way, better way of doing it, or a different way of doing it. So remember, if you have a bioreactor landfill, you're going to get more gas, but you're going to get it for a lesser period of time. However, you'll have more leachate. So there will be a cost of treating that leachate because you cannot infinitely recirculate the water. So bioreactor landfills can stabilize faster, and faster doesn't mean they'll stabilize in 2 years. They may stabilize in 5 to 10 years, and ordinary landfills may stabilize in 20 years plus. The same amount of gas is going to come out. So it's not like the quantity is same, because the reaction is going to give you, one will come out faster and one will come out slower. In the end, energy recovery is all about rate of return on investment. So if you are a owner of a gas production facility, you want to know how much money do I invest, how much electricity do I get out of it, and when I put it on the grid, how much can I sell it for, and do I get my return on investment. So wherever there is no return on investment, this is a non-conventional energy, you can get a subsidy from the government. But for long-term sustainability, subsidy doesn't work. For example, at the moment we are talking of solar power. It has become pretty cheap, but still I understand there is a subsidy involved in it. For solar power to survive by itself, when it is in the non-subsidized mode, then what is the rate at which electricity will be produced? Same thing here. If you can survive this on a non-subsidized mode, then it will be there for a longer period of time. Right? Any questions? Okay, have a good day. Enjoy yourself.